Alright, this video is going to illustrate the details of the pH titration for HONH2 in the flask titrated by HNO3, which is going to be in the burette. So first just start out with a picture of things. So you would have maybe a beaker, and the beaker is going to have HONH2 in it, and then you have the burette with a stopcock and a tip. Of course, that's going to be lower down inside the beaker so you don't have splattering, but inside the burette is going to be HNO3, so nitric acid, and this is going to be 0.1 molar HNO3, and then inside the beaker, the HONH2 is going to be 0.2 molar, and there's 50 milliliters of it. So the reaction is going to be the protonation of the HONH2 by the HNO3, and so do it in a different color here. You have NH2OH, so it's just like ammonia, NH3, except there's an OH group there instead of a hydrogen on the left hand side, and then the HNO3 reacts with it and is going to protonate right there where the lone pair electrons are to form HONH2, and then you get this extra proton there, and that becomes positively charged, and then nitrate is formed as well. So that's the details of the chemical reaction that takes place in the beaker. So we're starting out by looking at the pH associated with the HONH2 before any HNO3 has been added, and then we're going to add incremental amounts of HNO3, and we're going to calculate the pH. So the rest of the experiment would be to have a pH meter present here to be measuring the pH, and we want to compare that maybe to our calculated values. Alright, so then on the next slide we can start with part A, and for part A we have 0.0 milliliters of HNO3 added from the burette. So our reaction is just going to be HONH2 in water. So we're just looking at the hydrolysis of water here. This is an equilibrium with an ice table, and again, because this is the base, the water will donate an H+, and so it'll be ONH3 plus hydroxide. So there's no nitric acid added to this. This is just simple hydrolysis with an ice table. And we start with the concentration of 0.20 molar, molarity because it's an ice table, and 0 and 0. And in the end we have 0.20 minus X, X, and X. And I didn't tell you on the last slide, but we're given that Kb for HONH2, this would be hydroxylamine, by the way. HONH2 is 1.1 times 10 to the minus 8, and that'll be equal to x squared divided by 0.20 minus x. So we compare 0.2 to Kb to test for the ability to drop x, and so 0.2 divided by 1.110 to the minus 8 is greater than 100, so therefore it's okay to drop x here. Okay, that will simplify our calculation. And we're going to say x is equal to the square root of 0.2 times 1.1 times 10 to the minus 8, and that'll be equal to 4.7 times 10 to the minus 5. Now we go for x, we look at x here, and we go back to our table, and we see that x is equal to the OH minus concentration here. Take the negative log, and we're going to see the POH will be equal to 4.3, and I should have another sig fig there, but looking at my notes here, I don't have that extra sig fig. Moving on, then we say 14 minus the POH will be equal to the pH, and so the pH will be equal to 9.7. It would be good to have another sig fig in these calculations. All right, so that's part A. There's going to be 4 parts total. So now, and part B, now we're going to add 50 milliliters HNO3 from the burette. And now we're looking at the chemical reaction of HONH2 hydroxylamine plus HNO3 nitric acid, forming HONH3 plus NO3 minus. And this is a reaction, so we're looking at the reaction table before reaction, after reaction, and for this we need moles. So down below, let's go ahead and do a mole calculation. Moles of HONH2 are going to be 0.2 molar times 0.05 liters, which is 0.010 moles, and moles of HNO3. Could have done this first. Excuse me, 0.10 molar times 0.05 liters. And this is equal to 0.0050 moles. All right, then we come back to our excuse me, reaction table on the top. We're starting with 0.010 here, and 0.0050, and 0 and 0. And then, of course, when you're doing a reaction table, I don't always write this down, but you look at the smaller number, which is the limiting reactant, and you subtract here to get 0. You subtract here to get 0.0005, and then you add here to get 0.0005. And it's the same thing with the nitrate, but we don't even care about the nitrate because it has no contribution to the pH. But that's a basic stoichiometry problem. So you can just cross that out. We don't care about the nitrate here. All right, so if you look at this, hopefully you'll see that you have, let me get another color here, green maybe. Hopefully you'll see that you have quantities of both the base and the conjugate acid. So that's going to make it a buffer solution. All right, so then if it's a buffer, we're going to go ahead and use the Henderson-Hasselbach equation, and we are given the pKb. So let's go ahead and calculate pKa. So pKa for HONH3 plus is going to be 1 times 10 to the minus 14 divided by pKb, which is 1.1 times 10 to the minus 8. So we're going to have 9.1 times 10 to the minus 7. All right, then we can go ahead and use the Henderson-Hasselbach equation and go back to red here. Say that the pH is equal to the pKa, which is the negative log of 9.1 times 10 to the minus 7, and then pH is equal to pKa plus the log of base over acid. Now you can either take the ratio of the moles of base over acid or the ratio of the molarity of base over acid, molarities. Doesn't matter because the volumes of the molarities will cancel. So since we have the moles in green on the top, circled in green on the top, we can use that. So it'll be 0.0005 divided by 0.0005, and we'll end up with pH here being equal to 6.0. Again, one more sig fig would be desirable here. So we have the unique situation where the acid and base concentrations are the same, so that's equal to 1. The log of 1 is going to be 0, so this whole term cancels out, and we end up with the very unique situation at the halfway point. We know it's the halfway point because we have half the amount of nitric acid compared to the HONH2, the hydroxylamine. And so we have that the pH is equal to the pKa at the halfway point, halfway to the end point. And that's important graphically. All right, so then part. And for part C, we have 100 milliliters of HNO3 coming from the burette. And now we want to calculate how many moles there are associated with that. And the number of moles is going to be equal to, let's see, we have 0.1 molar. So it'll be 0.1 molar HNO3 times 0.1 liters, which is 100 milliliters, and you get 0.010 moles of HNO3. All right, so now you can set up your reaction table for part C, which is going to be HONH2 plus HNO3 forms HONH3 plus NO3 minus, and then we've got before reaction and after reaction. We have 0.010 moles of each, so we know that this is the end point here. So if we subtract 0.010 here and here, we're going to get 0 and 0. We're going to add 0.010 and get 0.010 here and 0.010 for that. Now, here, you might not think so, but this is a salt. This is hydroxyl ammonium nitrate. And we always see the situation where we have a salt at the end point. And this looks messy here, but this is 0, 1, 0. So we have quantities of cation and anion that are the same. And cation and anion means that you've got a salt. So you have a salt at the end point. And now, because you have the HONH3, the hydroxyl ammonium ion is the conjugate acid of hydroxylamine base, you have the situation here where the HONH3, this one can hydrolyze water, and this is the one that will contribute to the pH. The nitrate itself will not. So at the end point, if it's a weak system, you always have to do a little bit more work. There's a second table that you have to do. And, excuse me, the next step would be to take HONH3 plus and just let it hydrolyze water. And because that's an acid, the HONH3 plus is an acid, that means it's going to donate H plus to water, and so it'll go back to the base, HONH2, and hydronium will be formed. So that means if you got hydronium on the right, that'll be an acidic solution. Alright, so now we have an ice table to do, and we need molarity for that. And so at the bottom here, let me just do a quick calculation on molarity. So you have 0.010 moles of HONH3 plus. Now we're going to divide by the total volume. We have 100 milliliters of nitric acid, and then we started out with 50 milliliters of the base in the beaker. So there's a total of 150 milliliters associated with this endpoint. Okay, so we're going to say 0.150 liters, and that'll give us 0.067 molar, and that's what's going to go here. 0.06, oops, forgot the zero. Not good. I don't know if I can erase or not. Let me try. Yep, I can. Sometimes I can, sometimes I can't. So 0.067, and here you have 0 and 0. This is an ice table. So you're going to have 0.067 minus x, x, and x. And this is an acid problem, and so you need Ka for this. And so we're going to use Ka, which we calculated as 9.1 times 10 to the minus 7. And this is going to be x squared divided by 0.067 minus x. Drop the x, and then finish it off. Ka, so this is going to be the H3O plus concentration, which will be the square root of 0.067 times 9.1 times 10 to the minus 7. And let's see if I can squish this down. Yes. Then the H3O plus concentration is equal to 2.5 times 10 to the minus 4 molar, and the pH will be equal to 3.6. So at the end point, it's acidic. The salt itself is acidic. Alright, then we have one more to do, and that will be the after endpoint situation. And D corresponds to 150 milliliters. This actually comes from a group activity which originally read 125 milliliters, so this may be different if you're comparing it to a group activity that we did. 150 milliliters of HNO3 added from the burette. Okay, so we want to calculate the number of moles for this, and it's going to be 0.1 molar HNO3 times 0.150 liters. So that's going to be 0.0150 moles of HNO3. Okay. So then our reaction is going to be HONH2 plus HNO3 forms HONH3 plus NO3 minus. And we want to do a reaction table here, before reaction, after reaction. And we always start with the same amount of HONH2, the hydroxylamine, which has always been the same in the beaker. So 0.010 moles. The HNO3 is 0.0150 moles, 0 and 0. And then we're subtracting the smaller one, the limiting reactant, to get 0, subtracting to get 0.0050, and adding here 0.010. And same thing with nitrate, but again, we don't care about it. Alright, so the issue here is you have an acid that has some concentration, and then you have a conjugate acid that also has some concentration. And I've mentioned this in class several times. The conjugate acid here will hydrolyze water, so HONH3 plus water will go back and form HONH2 plus H3O plus, and so there will be a acidic pH associated with that. But numerically it's going to be very, very small compared to any contribution of the H plus from the strong acid, because you get 100% association here. Okay, going this way you got to use a value of Ka, and so your concentration is going to be somewhere around 10 to the minus 5 for the H plus. Over here it's going to be 10 to the minus 3, so it's going to be much larger. My advice to you is just ignore the H plus concentration from the conjugate acid and just worry about the strong acid. So the last step here would be to figure out the molarity for the HNO3. So you'd say concentration of HNO3 is going to be 0.0050 moles divided by 150 milliliters plus the 50 we started with, so it's going to be 0.2 liters, and this is 0.0, can't read my writing very well there, but I think it's a 0.028, whoops, let me change that, sorry. I think it is a 0.028 molar, maybe you want to check that. And then you get 100% dissociation of the HNO3, so that means the H plus concentration is the same, and so the pH is the negative log of 0.028, which is going to be equal to 1.6. So that's the final answer for the last step. This is beyond the endpoint. Alright, and then on the last, look at a graph, just a sketch here. And so this would be a summary of the points that we calculated. And this is a graph of pH versus milliliters of HNO3 added. And we have 0, 50, 100, 150. And our pH could be 2, 4, 6, 8, 10, for example. So let's see, we started out with a 0 milliliter HNO3 and a pH of 9.7. Hold on. Okay, 9.7 here. And then if after 50 milliliters were added, there is a pH of 6. That is the number 6 right there. And then 100 milliliters, the pH was 3.6, so it's somewhere around here. 150 milliliters, the pH was 1.6. So it looks like it just a nice little curve, but if you had more data points, you'd see that it comes down and then it's going to do something like this. So you'd need more data points for that to see. So the end point is here. And remember, that's the salt. This is the halfway point. Oops. And this is where the pH equals the pKa. So at 50 milliliters, the pH equals the pKa here. So experimentally, you could figure out the halfway point, and you could come over and you say, okay, well, that's the pH that I read from the graph is equal to pKa. You might not know the pKa, for example. You could figure it out that way. Okay, and then this is just straight hydrolysis of the base. So that's just not an acid-base reaction. It's just hydrolysis. And then over here, this is just straight acid, strong acid. And then also, I pointed out in class that in this region, this is all the buffer region. You can use Henderson-Hasselbach equation all the way through that region. And then after the end point here, it's all just strong acid. And at the end point, of course, you have the salt. So, all right, hopefully that helped. This was taken from a group activity that you guys had for Chem 102. Thanks.